session, we are going to see about concurrency and synchronization. A warm wishes to everyone. So far, we have seen about the process schedulings and completely about the process, and we are moving to process synchronizations and how concurrently the process can execute using various techniques. Myself, Dr. Shirisha, Associate Professor from Department of CSE, MLR Institute of Technology. So, concurrency and synchronization. So, what is concurrency? Process can execute concurrently, which means parallelly at the same time, and may be interrupted at any time, partially completing their execution. So whenever we use a preemptive algorithms, we have seen the SJF preemptive and priorities also. So based upon the time slices in the round robin also, so where you are preempting, stopping the process in between. So that is concurrent access to shared data may result in data inconsistency. Whenever you are parallelly executing, so when you are sharing the data to every process, so it may result in the data inconsistency. Everyone will get their own results. So one result may not be equal to the other result. So what is happening whenever you are sharing data? So it should be centralized, and the output also, if it is same, then we can say they are doing the concurrent process. When the multi-process are executing and multiple outputs you are getting, there is no concurrency. And maintaining the data consistency requires mechanisms to ensure orderly execution of the cooperating process. Cooperating process means what? Whatever the process you are executing, if you have 10 process ready in the queue, and all the 10 process should undergo its execution within the process, so that processor should be capable of handling all these processes which are in the ready queue or the waiting queue. So how you have to manage? So you should have a consistency, you should have concurrency between them. So what is that problem is, suppose we wanted to provide a solution to produce a consumer problem that fills all the buffers, and we can do so by having an integer counter. So you have a counter which points to the next instruction, and you have a buffer. So whenever you have a producer, whenever the buffer is empty, the producer can produce an item. So he can produce item 1, item 2, item 3, item 4. So now the buffer is full. Whenever the buffer is full, the producer cannot produce any more items there. Now the counter, why we are using counter is, the counter increases, or if you are giving the counter as 4, until the counter reaches 4, it can produce how many items? 4 items. Now after producing all the 4 items, now the producer cannot produce any item because the buffer is full. Now what? The consumer has to consume the item. Okay. Now if the consumer has consumed this item, there is one more space in the buffer. Now the producer can produce one more item in the queue. So like that, you need a counter to indicate what the counter has to whether the producer has to produce an item or consumer has to consume an item. To understand this, we need a counter. So initially counter is set to 0. It is incremented by the producer after it produces, and it is decremented by the consumer after it consumes. So by keeping this in mind, we will see a simple producer consumer problem we have discussed in the previous session also. Just I'll give a quick review of what is producer here. So whenever there are some items to be produced, then produce an item in the next produced. Okay. So while counter is equal to buffer size, then do nothing. Then counter means what? If your counter is 4 and the buffer size is 4, then it is empty. You should make them empty. So to make it empty, we are going here. If it is not empty, we are stopping the process then and there, because producer cannot produce any item. Now once it is empty, the buffer in. So first, if there is a here and your buffer is indicating here, this is buffer of in. That means say in is 0, buffer of 0. Here it is producing the item, say I1. Then what happens? In plus 1 percentile buffer size. If the buffer size is 4, so what is in? In is 0 initially, if you have initialized it to 0. So 0 plus 1 is 1. 1 percentile 4. Okay. So when 1 percentile 4. So 0 percentile 4 is what? So you are getting a remainder as 4. So what is this? 0 plus 1, 1 percentile 4. Okay. So 1 percentile 4 is what? You are getting 0. So when in is 0, your buffer is producing an item and the counter increments to 1. Whenever the counter increments to 1, the counter becomes 1 here. Now what is in? In is also incrementing to 1. So in of 1, now the item can be produced here. Now until and unless the counter reaches the buffer size, it becomes empty. Now the counter is 1, it is producing. Counter is 2, it produces the next item. Counter is 3, it produces the next item. So until and unless your counter is 4 and the buffer size is also 4, now the buffer is full, the producer cannot produce any item. Therefore this while loop will not produce any. This while loop will make no producer to produce an item because the buffer is full. Now what we have to do when the buffer is full? Now the consumer has to consume the items. In the consumer, what we have to do? Now counter equals to 0 is initially. If counter is equals to 0, do nothing. Counter 0 means here. Counter is 0 means your producer has to produce here only. Now there are no items here. When the buffer is empty, can the consumer consume any item? No. Now when the buffer is full only, you can consume. So counter should here it should be 4, means equal to the buffer size. That means all the items are there. I1, I2, I3, I4. So when all the items are there, the next consumed is equal to buffer out, means whatever buffer of 0 you are indicating initially, this is consumed. Okay. After this, again it will go to the next position. So here out is equal to out plus 1 buffer size. So 0 plus 1, 1 percentile, the buffer size, 4. Okay. Similarly, again it increments, 1 plus 1, 2 percentile, 4. Like that, whatever the result you get, so it will go to the next process and the next items get consumed. In that way, it will repeat until your counter becomes 0. So if the counter is equals to 0, then you have no items in the here. So all the items will be consumed. Now there are no more items to get consumed. Therefore, again the producer now can produce an item since the buffers are empty. So like that we have to decrement the counter value in terms of a consumer, and you have to increment the counter value in terms of the producer. So when this is the situation, we have a drawback of race condition in the producer consumer problem. What is race condition? Counter plus plus can be implemented as, so counter plus plus, if it is given like this, so we have register 1 and which is the counter value, okay, and register 1 is equal to register 1 plus 1 and counter is equal to register 1 we have given, and counter decrement could be implemented as these instructions. Now see here, if consider this execution interleaving with count equals to 5, initially count is 5 that is given, producer execute register 1 is equals to counter, means the first instruction here. So register 1 is equals to counter means what is register 1? 5. Now in the next instruction, next set of instruction, producer execute this second instruction cycle. Now the register 1 is 6 because we are incrementing it with 1. Now in the next, consumer executed, register 2 is equals to counter. That means this one. Okay, this is 1, this is 2, this is 3, 4, 5, 6. Now here we have executed 1 and 2, but after 2 what we are executing? We are executing 4. So when we are executing 4, what is register 2? Counter. What is the counter value? 5. Now register 2 is 5. Now what is happening here? This is the instruction 5. So what is register 2? We are decrementing the value. So 5 minus 1, 4. Now when after this, what we are doing? We are doing counter equals to register 1, that is 3. And here 6. So 3 and 6 are executed. Now in this case, what is register 1? 6. Now see what is the counter? 6. In this case, what is register 2? 4. Now what is counter? 4. But according to the instructions, if you take like this, okay, 1, 2, 3 and 4, 5, 6, what happens? So 1 if it is executed giving 5, 2 if it is executed giving 6, and after that 3 if you execute, what is the counter now? It is 6. Now here if 4 is executed in the sequence, what is the counter value? 6. 6 is given to register 2. Now register 2 is 6 and 5 is again register 2, that is decremented, so 5, and now what is the counter? 5. But counter value here and here are differentiating. Now whenever you are changing the set of instructions, the sequence, so you are getting a different outputs. So that condition we are calling it as a race condition, where it is not giving the accurate results. To avoid this, we have different techniques and we are moving to critical section problem. So we have a producer consumer problem. The producer will produces the item and the consumer will consume the item. To produce an item, the counter will get incremented. To consume the item, the counter will get decremented. So you have a condition called race condition, where the set of instructions that you are executing should be appropriate. Therefore, if you change the sequence, it is giving a wrong result. So this sort of problem, we are calling that as a race condition in the producer consumer problem. So next, moving further, we are going to critical section problem, where you have n number of processes. If a process is, there are 10 processes, so it starts from P0 to P9. So each process has its own code segment, that's a critical section code segment, and a process may changing common variables, updating table, writing files, etc. When one process in critical section, no other may enter into the critical section. That means what? If a process is there, a process has entered the critical section, means allocated the processor. So it is in the critical section now. So whenever this is executing in the critical section, if say this is P1, the process P2 will be in the waiting state now. Now P2 has to execute and allocate the processor. Can that possible? No, because this P1 is already in the critical section. You cannot allow any other process to enter into the critical section. So this is where critical section problem is to design the protocol to solve this. Okay. So when one process in the critical section, no other may enter into its critical section. So each process must ask the permission to enter the critical section in the entry section. So here you will have a entry section and may follow the critical section. This is critical section where execution is happening, and outside this, whenever after completion of process P1, it has to come to exit section and it will check the remainder section whether you have any other process which are there in the ready queue to enter into the critical section. So they are ready to enter into the critical section now. Since this has come to the exit section, now if you have P2 in the remainder section, now P2 can come into the critical section and it executes its process. So like that, how many processes we are executing at a time? Only one process. This is a critical section problem. So how does the structure here? So as I told you, whenever there are processes in the queue, so while of true means wherever you have a process, the entry section, the process will enter the entry section, then to critical section. After the completion of the job is completed, then it will go to the exit section. Then it will see what is the remainder section and it will enter the critical section. Like that, the loop will get repeated. So this is the structure for I number of processes. So what is the algorithm for this is, now while turn is equals to j, so algorithm for process pi. So process pi, okay, while turn is equals to j, do nothing, okay, it is not entering into the critical section. Okay, now who is having a turn equal to j means no. Where it is not equals to j, you have I. Now who is in the I? Critical section, process pi will be in the critical section. Now after the completion of this critical section process, it is giving the turn to j, means the next process. So next process is j, and now what it turns in no process, the remainder section you will be having j only. Now while of turn equals to j, now j will go to the critical section. So what is happening here? It is whenever your process is entering the critical section, it has to give the turn to j until and unless turn is given, and this condition it has to satisfy that turn is equals to j, then j has to enter into the critical section. So this is algorithm or the structure for process Pi to get executed. So based on this, we will see the techniques that are there for providing the synchronization. So solutions to critical section problem. So we know what is a critical section problem, saying that only one process at a time can enter the processor. So that's a critical section problem. So what is the solution here is mutual exclusion. Mutual exclusion. If process Pi is executing in the critical section, so critical section is within the blocks and no other process can be executing. So this is what we call it as a mutual exclusion. Yes, mutual exclusion is achieved. Progress. If no progress is executing in its critical section, there exists some process that wish to enter the critical section. The selection of processes that will enter the critical section next cannot be postponed indefinitely. That means what? If you have no, here in the critical section, there is no process in the critical section and you have some other process in the ready queue where they wants to enter into the critical section and so whether that is P2 to enter or P3 to enter. If P2 you are giving, so P2 continuously you cannot give the chance for P2. So P2 has to complete its job, then come out of the critical section. Then P3 has to enter. Now the chance has to be given to the P3. So there should be some progress between the process. You cannot give always a chance for P2 and P2 continuously can execute in the critical section. That is not possible. So this is called progress. Bounded waiting. So as the name indicates, a bound must be a limit. A number of times that a process can execute, for that you are giving a limit. A bound must exist on the number of times that other processes are allowed to enter the critical sections after a process had made a request and to enter its critical section before that request is granted. So they have to wait until that process which is there in the critical section will complete its job. So assume that each process executes at non-zero speed and no assumption concerning relative speed of the end process. So we are assuming that a process is executing until its burst times are given, and once the burst time is completed, if it is FCFS, until and unless the burst time is completed, you cannot give the chance for the next process. So this is how bounded waiting is achieved. Okay. So these are the three conditions that you have to check where this is the solution for the critical section problem. If there is no progress, you have to preempt it. So there should be a progress so that critical section problem can be avoided. And bounded waiting, the number of times you are allowing the other process into the critical section, that should be limited. So if you are continuously sending the process and you are continuously making the process to wait, then it will be leading to starvation. So to avoid such things in the critical section problem, the solutions for critical section will be mutual exclusion, progress and bounded waiting. So critical section handling in OS, there are two approaches depending on if kernel is preemptive or non-preemptive. So one approach is preemptive and the other one is non-preemptive. Preemptive allows the process when running in the kernel mode. Non-preemptive run until exits the kernel mode or blocks or voluntarily leaves the CPU. So this is essentially free of race conditions in the kernel mode because the process once it is entering, it is completing its job. You are not preempting it. Therefore, there is no chance of changing the sequence or of the order of execution of the process. Thereby, it is essentially free from the race condition problem, which we have discussed in this session. Okay. And we'll see, to achieve concurrency, what is Peterson's problem? Peterson's solution. So for the critical section problem, one of the solution is a Peterson solution, and this is just a description of how you solve the critical section problem. There's a two process solution. So if you have Pi and Pj, so this is a two process solution which is a Peterson's solution. Assume that load and store machine language instructions are atomic. Okay, and that cannot be interrupted. Okay, they cannot be interrupted. So two processes share two variables. So one is a turn and the other is a flag. So how many flags means two, because we are having two processes, Pi and Pj, and we are changing the turns based on the requirement. So the variable turn indicates whose turn to enter into the critical section. So whether it is the turn to I or whether it is turn to J that it is entering the critical section. So to know that, we are giving a turn as a variable where it decides which process, whether I or J, has to enter the critical section. The flag array is used to indicate process is ready to enter the critical section. Flag of I is equals to true implies what? Pi is ready. If Pi is false, that means what? Now flag of J is true. That is the meaning. Okay, now Pj can enter the critical section. So that is the meaning. So to know which is having a turn, we are defining the turn and flags. So we'll see the solution with the help of a small code. So this is the algorithm for process I in a Peterson solution. So what Peterson solution is saying that if there is any process that is waiting in the ready queue, now how many processes will be there in the ready queue? One is I and the other one is J, because this is a two process solution. Now flag of I is equals to true. Initially what is flag of I? Yes, it is true. But what is turn? Turn is given to J. When I is true, turn should be also to I. But what I is doing, it is giving the turn to J. So when turn is given to J, now we have to check the condition. Whether the flag of J is true and turn is equals to J. Flag of J. What is flag of J? Flag of I true means what? Flag of I is executing. But flag of J is false here. Because already flag of I is true. Because this is a true process solution, when one process is true, the other process is false obviously. Now, and turn equals to J. Yes, turn is equals to J. This is true. Okay. What is the logical and logic table? So, this will be true, 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 false, false, false and false, true. Okay. False, true and false, false. If both the conditions are true, then only it is true, otherwise all other. If one is false also, the condition is getting false. Now you have one condition as false. When the condition was false, can it enter the critical section? No. So which can enter the critical section now is the question. So since the flag is I cannot enter the critical section because you are giving the turn to J. Now critical section, okay, which process will execute in the critical section? J process will execute in the critical section. Now flag of I you are becoming false. So whenever the flag of I is getting false, you have to make flag of I is false, then only it can go to the next process, that is the Jth process. Now what do you understand by this condition? Flag of J is false, okay, and this is also true. When the condition is false, then it is entering into the critical section. If the condition is true, then when the condition will get true? Flag of J true aval means and flag of J is true and this is also true. Now which will enter the critical section? J will enter the critical section. Whenever this condition is true, both are true, you are doing nothing because I is not entering the critical section. This is true and this is true. Whenever condition is true, you have a semicolon here. That means which has to execute? J has to execute. But J is not entering the critical section. When it enters the critical section, only when this is false. So, when this is getting false, so I should enter the critical section. When I is in the critical section, you have to make the flag of I as false because it is initially true. Until and unless this is false, what will be in the remainder section? J will be waiting in the remainder section. So, J has to again get a chance here. So, when J will get a chance, whenever both are true, then J will get a chance to enter into the critical section. Okay. So, this is how a solution we are giving for a Peterson, the critical section problem. Even though the turn is for I or the flag is true for I, we are giving chance for J for execution. In this way, we are not blocking the critical section to execute always only the ith process. So, it is giving chance for or the turn for jth process also. This we are calling this as a Peterson's solution. So provable that three critical section requirements are met. What is that? Mutual exclusion is preserved because how many processes always is entering into the critical section? Only one, either I or either J according to the conditions. So which is where you are executing what? Mutual exclusion. Now after execution of I, you are having progress also. You are giving a chance for J also, and after J, you are giving a chance for I also. So in this way, progress is also achieved. So Pi enters the critical section only if Pj is equals to false or turn is equals to I. Then only Pi can enter. If Pj is becoming true, who is can enter into the critical section? Jth process can enter into the critical section. Now progress requirement is satisfied because both I and J at one time or the other they are entering the critical section, and bounded waiting is also met when I is executing, J is waiting, but it is not waiting for a longer period of time. So we are, once the I is coming out, we are making J to enter into the critical section where bounded waiting is achieved. Bounded means a limit, number of times you are calling the process, that limit is bounded. So that bounded waiting is also achieved. So when these three are achieved, these three are the solutions. What is that? Mutual exclusion. Second one is a progress, and third one is a bounded waiting. These three are the conditions to satisfy the critical section problem. So when we have a solution for Peterson's as a solution for critical section, it has to satisfy these three conditions. Hope you all understood what is Peterson's solution. Thank you all.